Have you ever wondered how apps like your favorite social media or gaming platforms manage and organize vast amounts of data? Well, the secret lies in data structures. Welcome back to my channel. Today we are diving deep into linear data structure, a fascinating category of non-primitive data structure that plays a pivotal role in how we handle information. Non-primitive data structures can be further categorized into two types: linear and nonlinear structures. Let's break this down. First up, we have linear structures. In this structure, elements are arranged in sequential manner, where each element is connected to its previous and next element, which allows to perfectly traverse in one direction. Now, let's look at the different types of linear data structures. The first one is an array. An array is a data structure that stores a collection of elements typically of the same type in a contiguous memory blocks. What exactly is an array? Imagine a row of boxes, each capable of holding a piece of information. This information can be numbers, characters, or even objects. But here is the catch. They are all typically of the same type. Let's break down some key characteristics of an array. The first one is indexing. Each element in an array can be accessed using an index. Most programming languages use zero-based indexing, which means the first element is at index 0, the second element is at index 1, and so on. So, if you want the first box, you would grab the one at index 0. Next, we have fixed size. When you create an array, you define its size in advance. It can't change dynamically in languages like C or Java. But don't worry, in languages like Python, you can resize your array, making them a bit more flexible. Now, let's talk about homogeneous elements. Arrays typically store elements of same type. So, if you decide to create an array of integers, all boxes will hold integers. No mixing or matching is allowed in this data structure. Finally, due to their contiguous memory allocations and index-based access, arrays provide efficient access to their elements. This means if you know the index, you can quickly retrieve the information stored there, like grabbing a specific box from a row. Why do we love arrays? Because they let us to access our items super fast. Whether you are storing numbers, names, or even your favorite memes, arrays are your go-to solutions. Now, go ahead and start experimenting with arrays in your favorite programming language. The second type of linear data structure is a queue. It is a type of data structure that follows first in, first out method or principle. This means that the first element added to the queue will be the first one to be removed. Imagine you are at a coffee shop. The first person to place their order is the first to receive their drink. That's exactly how a queue operates. It ensures that the first element added is the first one to be removed, maintaining order and fairness. And this data structure allows us to perform basic operations at two ends of a queue, a front and rear. A front is the place where elements are get removed. A rear is a place where new elements are added to the queue. Think of like a line of people. New arrivals go to the back and the person at the front gets served first. Now, let's talk about some key operations you can perform on a queue. First, enqueue. The enqueue operation is used to add a new element to the rear of a queue. When we want to call an enqueue function, we provide the item we want to add as a parameter. This ensures that the new element joins the queue at the back and maintaining the proper order of elements. So, when you call enqueue, you're simply saying add this item to the end of the queue. Next, we have dequeue. This operation removes an element from the front of the queue. When we call dequeue function, we don't need to provide any parameters. This is because the dequeue operation is specifically designed to always remove the front element, the one that has been in a queue for the longest time. So, When you call DQ, you are simply saying remove the first item in line. This keeps the queue moving smoothly and ensures a fair process for everyone waiting. Next, we have peek. This operation allows you to view the front element of a queue without removing it. When we call peek function, we can check which item is at the front, but the item remains in a queue for future operations. So, when you call peek, you are simply saying show me the front item but don't remove it. This is useful for understanding the current state of a queue without altering it. Next, we have is empty. This operation checks whether the queue is empty or not. When we call this function, it returns a boolean value true if there are no elements in a queue and false if there are one more elements present. So when we call is empty, you are simply asking is there anyone in a queue. This operation is essential for managing queue effectively and ensuring that operations like DQ and peek are performed only when there are elements to be processed. Let's look at a quick example to illustrate how these operations can be performed. Here we start with 3 elements in our queue, 1, 2, and 3. Now we want to add a new element to our queue, which is number 4. So we'll use enqueue operation together with the items to be added as a parameter. This enqueue operation adds the item to the rear of the queue, and the new queue after enqueue operation will hold 1, 2, 3, and 4. Now, if you want to execute DQ operation, this DQ operation will remove the first or the front element, which is 1. So, after executing DQ operation, our new queue will be 2, 3, and 4. So, after this operation, 2 is now the front element of the queue, which is ready to be processed next. This example demonstrates how enqueue and DQ operations work in a queue, making it easy to manage the order of elements. In summary, queues are super useful. They are used as task scheduling in operating system, managing print jobs, even in algorithms like breadth first search. The possibilities are endless. Let's shift our focus to the other type of linear data structure, stack. Stack operates on a different principle compared to queues. While queue uses a first in first out approach, stack uses last in first out method. This means that the most recently added element is the first one to be removed from a stack. Let's dive into the key characteristics of stack. First up is LIFO order. The most recently added element is the first one to be removed. Think of it like a stack of plates. You can only take the top plate off. Next, we have 2 main operations on a stack, push and pop. Push is used to add an element to the top of the stack, and pop is used to remove the item from the top of stack. Like enqueue operation in a queue, when we call push, the item to be pushed onto the top of stack will be given as a parameter. Next, we have peek or top. This operation allows you to view the top element without removing it. And finally, we have is empty. This checks whether the stack is empty or not. Consider a stack of numbers. When you perform a push operation to add number 4 on the top of stack, the stack now becomes 1, 2, 3, 4. With our stack top points to the new recently added element, which is 4. If you then pop the stack, you remove 4, leaving you with 1, 2, and 3. As we have discussed previously, the pop operation will remove the most recently added item onto stack. Stacks are fundamental data structure in various algorithms and applications, like managing function calls in programming, undo mechanisms in applications like text editors, and evaluating expression and syntax checking, making them essential for a programmer to understand. The other type of linear data structure is linked list. So, what exactly is linked list? Linked list is a data structure where elements known as nodes are stored in a sequence. Each node in a linked list has two main parts, the data and a pointer. The data is a value you want to store, like numbers or strings. The pointer tells you where to find the next node. So, if you think the data as a random item, the pointer is your map guiding you to the next item. Let's look at the key properties of linked lists. First is node structure. Each node contains two parts, the data, which is the value or information stored in the node, and a pointer or link, which is a reference to next node in a sequence. Next, we have dynamic size. Linked lists can easily grow or shrink in size by adding or removing nodes, unlike arrays which have a fixed size. And finally, we have non-contiguous memory. Nodes are scattered through memory and each node points to the next one, allowing for flexibility. So, why should we care about linked lists? They are incredibly useful. You can dynamically allocate memory, implement stacks and queues, and even manage undo mechanisms in applications. In addition, if you want to perform efficient insertion and deletion, linked lists provide a flexibility than arrays.